Hi, it's Group 33. 李作、陈果按左一点. This is AtomFlow, a CUDA and a CPP inference engine we wrote from scratch. It runs Llama 3.23b on a consumer RTX 5060 Ti at about 66 tokens per second, using only 5.5 gigabytes of the 16 gigabytes card. Unlike server framework like VLLM, which optimize for throughput, AtomFlow targets the single user case, one GPU, one request, batch size 1. In that regime, the bottleneck is not compute, it is memory bandwidth. In the next 10 minutes, we will explain why that matters, show a live run, and walk through what we learned. Large language model inferences has two phases. Preview process the prompt. It is compute bound. Decode generates one token at a time, and at batch size 1, it is strictly memory bound. Here is the roofline of our GPU. The reach point is about 52.9 flops per byte. But at m equals 1, the decode step has an arithmetic intensity of 1 OP per byte. That is 2 orders of magnitude below the reach. The single fact drive every design decision in AtomFlow. We call it physics first. Server framework like VLLM are built for the opposite regime. Massive concurrency, page attention, Python control panels. At batch size 1, every abstraction they add becomes overhead. Address transcation, kernel loss, latency, allocation chunk. We call this flexibility tax. Our hypothesis is simple. If we delete the flexibility we do not need, we can get closer to the roofline on a consumer card. I'm here to introduce our 4 important design decisions. The first one is static arena allocator. We know every tensor size at the compile time, so at startup, we make exactly 3 CUDA model calls. 1. Wait pool, activation pool, and keep catch pool. And you can find the full derivation in our report. So our aim is to make 0 allocations during inference. No fragmentation, no allocator calls on the hotspots. Second, and this is our biggest one, a fused W8A16G memory kernel. The naive parts dequantize the FP8 weight into a 48 megabytes FP16 spread buffer in DRAM. Then run a standard FP16G. Every projection pays a full round trip of bytes that carry 0 information. Our kernel reaches the FP8 weight directly, dequantizes it inside a register, and does the dot product immediately. The FP16 intermediate never touch DRAM. Results: the activation arena dropped from 49.5 MB to 1.5 MB. Third, a contiguous, arithmetically addressed keep cache with a custom group query attention kernel. No page tables, accessing position T, head H is one integer multiply n. Because m equals to 1, the Q matrix is a single row. So the kernel is short. 1 warp handles 1 attention n. The first one, CUDA graph capture. A decode step fires around 300 kernels, as you can see here. Each launch costs a few microseconds of GPU overhead. So we captured the entire forward path into a single CUDA graph and replay it once per second. Capture removes all. Now, let's enter our lifetime. First, let me show you the tree of the files. As you can see, this is the actual source tree. in the code filter, in the core filter, holds the engine and memory plan. In the kernel filter, holds CUDA kernels like GMV, attention, RMS norms, weak loose, sampling, etc. The whole engine is about 3,000 lines of CUDA CPP codes. And then let's run the inference process by this run inference. And let me summarize these headline numbers. First, we have achieved 60 tokens per second graphical on Llama 3.2. 2. The total VRAM footprints is no more than 5.5 gigabytes. That leaves 10 gigabytes free on a 16 GB card for the OS, the desktop, a browser, whatever. And third, the activation arena is 33 times smaller than a naive implementation. 49.5 megabytes down to 1.5 megabytes. That did not come from clever math, it comes from refusing to materialize intermediates. And most importantly, we have shown that we can beat BLAM and a fair single stream configuration. And here's our key findings. Our first finding is that the cost of software abstraction is measurable. And at m equals 1, it is not small. We isolated a second CMake target. Here, AtomFlow server tests as a sandbox to eventually implement page attention on our own kernels, so we can quantify exactly how many microseconds per token and indirection layer costs. The important point is not the number. It is that the framework should let the user pay the text only when they need the flexibility it buys. Our second findings, DoD transfer from gaming engine to large language model inference. Our second finding is that data-oriented design principles from gaming engine transfer surprisingly directly to large language model inference. The plain old data structs, static allocation, cache-friendly layout, no virtual dispatch. These are 15-year-old lessons from graphic and physics simulation. Reapplied to transfer the code, they produce a 10% speed up over a far more sophisticated framework. And AtomFlow is open source under the MIT license at github.com/autosig/atomflow. One command, the run inference.sh, reproduce array number in this video on any RTX series card. Next step, the page attention measurement in the sandbox and weather fusion coverage on the MLP paths. Thank you for watching. Questions welcome.